So welcome everybody to another Earth2Class program. We're pleased to be joined once again by Susanne Straub, and she's been with us several times. We enjoy listening to her work on what's happening beneath the surface with magma. So Susanne, you're on as co-host, and you can start your show whenever you want.
Yes, I'm start sharing. Oh, here we are. I have, yeah, I got a new NSF project funded. That was very nice, a very nice surprise last year. And the title, the object of this project is looking deep into the mantle root of volcanoes. Uh, I have talked about these things a little bit before, and you probably see something during the presentation you have seen before, but I will definitely also share a few new things. So the first thing what I want to emphasize, why we are motivated to look into the roots of these volcanoes. Well, I'm studying the explosively eruptive arc volcanoes that are major geohazards. I mean, you get like a volcano like Kilauea is constantly eruptive, but it's usually not explosively eruptive, and it's a nuisance, but it's not an immediate danger. But we have in the Ring of Fire, I'm sure you heard about that in Arc volcanoes. There are many that can erupt explosively. And these are still ticking time bombs that have caused in the past and will cause in the future major destruction to human life, to habitat, will also influence the climate in the short range. We have a lot of active research in monitoring such volcanoes and improving the forecast and mitigation, but still, we need to understand how these volcanoes work from melt formation deep into the mantle to the ascent and to the eruption, and that's where my project is going in. You see a cartoon here on the right side. On the bottom is the mantle. So the cartoon is covering the crust that overlies the mantle. We know the magmas come from the mantle, and you see all these colorings, this light yellow. They presumably still have low silica content, and then they get the silica content gets higher. The melt polymerizes more, gets more viscous, and finally erupts explosively. And we are not really sure about that because whether the silica melts really are created only in the crust or come in part out of the mantle. And so if we had more silica rich coming out of the mantle, it would change the whole prediction how these volcanoes are going to erupt. So in order to know that, we need to go, oh, yeah, here's my laser pointer. So I'm just, the scale of the rock, how to do this. This is what we normally see. A volcano here sitting on the surface of the earth is fairly small, and this cartoon is now showing the scale. We have the volcano on the top. The red one is showing the deepest hole drilled on Earth, about 12 kilometers or 7 or 8 miles. We have the thick Earth crust that's solid and the melted coming somewhere out of the mantle. So how to look really into that region where these melts are created, and especially what the composition here is after on when the melt passes on the mantle boundary into the crust. So the problem is, of course, when the hot melt is generated here on the mantle en route to surface, it cools down, it precipitates minerals, crystals like olivine, like pyroxene, like plagioclase. It also gets mixed a little bit, it cools, it stagnates, and by the time it gets out here, it's quite thoroughly processed. And so what we are doing is we're picking the olivines, because these are crystallizing first in the melt and have most likely messages from the melt that directly come out of the mantle. And sorry, and this is where the project is really about. Olivines, we can collect them in the rocks. There are some samples that are olivine ferric. You see here these green points in the green rock, a very characteristic color. Here on the right side, the olivines are separated out. They have this typical olivine green color. We go to the field now, collect these rocks, get the olivines out, and then we mount them here. The circle here is about 1 inch in diameter, and you see here the single olivine crystal mount in a distinct patterns. And this one we take to the lab and start analyzing. This is now a close-up of one of these olivine grains. For the scale is here 0.2 millimeter showing, and you see this is and it's in light that shines, transmitted light that shines through the entire crystal, and you see these dark little inclusions here. These are chrome spinels, also very important because they also contain information on the origin of the melt and of course a large crystal. On the right side, it shows the same crystal. This is the light only coming from top. It's the incident light. And you see only some of these crystals, these light gray dots. These are now the olivines where they are sitting on the surface, because many of them are sitting deeper down, enclosed in the olivine. For example, this one here, it's certainly enclosed here into the olivine, or some of here on the left side. You can even see them as shadow here, but we need to have those that are on the surface because these we can reach in the analysis. So what I'm doing, I'm working with a group in France who specialize on the olivine analysis. And one of the methods we are using is with the electron microprobe analyzer, which is a non-destructive method. It focuses a beam of concentrated electrons on the surface of these olivines. And the beam has 1 or 2 micron in diameter. So for scale of 1,000 micron make up a millimeter. And we can get quite a range of elements out of this. So we get not only the olivine analysis, we get here shown the green point, we can also analyze the chrome spinel. So depending on what beam current we use, this is just the current, is concentrated, the focused electron beam has on the surface of that. So it changes a little bit, but you see 20 nanoamps, you get, these are so-called major elements in olivine. The most of the elements that really make up the olivines, almost 100% of the olivine consists of silica, magnesium, iron, well, and oxygen, of course. And then when we increase the beam current, we start to capture the trace elements, which are in very minor amount in that. And then in a very specialized probe that can run at 5 to 900 nanoamp beam current, we get more and more and more trace elements. And of course, we can also do the chrome spinel inclusion. A very important thing we can do with the electron microprobe, we can also map the olivines. And that's what I'm showing here. So these are 2 different grains of olivines, and you see this beautiful color. This shows the distribution of the element nickel in the olivine. There's a nickel-rich core with about 5,000 ppm nickel. And the chrome spinel inclusions are shown in green because they don't have so much nickel. You see the more greener and bluer the color gets, the lower is the nickel, and the rim, the nickel is maybe about 1,000 ppm. Yeah, the red one is a small sulfide inclusion. It's very red because it has a lot of nickel. And we see this beautifully sounding, or this is another example. And it's important to know where these sounding are. It has information, not only how high this nickel is, but also that this olivine grain crystallized in a changing environment where finally the nickel and it's finally in contact with melt that doesn't have so much nickel any longer. And oh yeah. And a problem is also, this is one of the same crystals here before. You see, while this core of the olivine is really wet, it starts getting a little bit diffusive here, and towards the green and towards the blue. And then the bottom, there's the same crystal that's analyzed for phosphorus. We made them up in phosphorus. And you see here in the center, these big sectors, they tell us that the olivine that has been grown very fast in the center. And it has grown so fast that we have in certain directions of this olivine, we have a build-up of phosphorus that where it gets green and then red and yellowish, so the phosphorus goes up. And because the phosphorus crystal is not, we call it isotropic, it does that's the crystallographic structure of it. It's not an isotropic one, it's a non-isotropic one. It doesn't grow equally in each crystallographic direction, and then it makes these sector sounding, which is very typically for fast-grown melt. And you see these very sharp rims here on the side, which really stand out to the more diffusive rims here from the olivine. And that simply shows that the phosphorus is very slow diffusing. So when the melt comes up, crystallizes olivine, and the olivine goes to the surface, and the nickel becomes depleted in the melt, and the nickel goes down. That is what this olivine is recording really greatly. But it also, as the olivine goes up, it tries to readjust to this changing environment. And the nickel is a fairly fast diffusing element, so it changes more quickly, while the phosphorus is very slow diffusing, and it's much, much better in keeping the original sonation, which is a very important thing, because we need also, of course, when the olivine crystallizes early, we need how it has changed till it finally comes up and the melt cools and crystallizes here on the surface. That's a piece of information. And the other thing is that we also need these maps for placing laser points. This is another instrument where we can analyze these olivine grains. We can analyze a much broader spectrum of them. They can have better quality. But the disadvantage is that while the electron microprobes, the first instrument is non-destructive, it makes holes here. The laser does make holes in the olivine and has much larger spot sizes, so between 38 and 100 micrometer, and not the 1 or 2 micrometer. I should say that I'm also working with that group here in France. They worked out one of the newer laser ICP-MS, a so-called triple quadruple. It's a very special instrument where you can sort out better the signals from the background, but it does require some mastery to run it, and setting it up with my French colleagues here spent a lot of time, and I feel actually very lucky that I can go to that lab. I have recently been to Mexico. My Mexican colleague at UNAM also bought a triple quadrupole from a different brand, and he is still in progress of setting it up, and he knows it's going to be very complicated. But in France, they did it, and they also specialize on olivine analysis, which is very good for me because I can just go there and obtain my data. So I mentioned that the laser is going to make holes, and these are other examples of olivine, nickel on the left, and phosphorus here on the right. And you see the holes by the laser. it's a little bit deceptive here. It does not really, the hole does not cut through the olivine. This white hole right now, it's only a deception of making this olivine colored. Anyway, but it goes in for several tenths of micrometer. And once we have analyzed the spot, it's so-called dead, so we cannot go into it. And you see also from the sonation, that's very important that we know where to put these laser holes. Actually, these holes, we first lasered it and mapped it afterwards to see where they are, where the laser went. And we met it fairly well. I mean, I should have probably gone here. You see a small sector sounding, this is probably outright the total core of it, but we hit it still fairly well. But you see, this can also go rather wrong while we put these laser holes fairly well in the middle of the crystals. It's only the sonation is telling us that we missed here the nickel-rich core. That's one thing we are really after, and ended up doing here in the rims. You see, it goes down from the red to the yellow to the green, and it goes into the dark blue and actually becomes a little bit lighter blue. So what that means is that the nickel actually goes a little bit up again and then finally goes down. This is very typically what happens when the olivine is sitting in this rising melt and goes up. It goes a little bit to the middle. And you see, but see again, beautiful is that the original phosphorus zoning is absolutely retained. So we know really in which direction it has grown. And we know that we have to go back to that olivine and really trying to re-hit the core. Nickel is an element that really comes out of the mantle. And that's why we always drive into the nickel and want to see these are the most mantle-like signatures we are going really here to have. So this is another example about zoning. You see, the zoning is not always simple that the core of the olivine is nickel-rich. We have, in that case, we have here the core that is outlined by phosphorus that is actually has this blue color indicating fairly low nickel. And then it apparently has grown to a high nickel. And finally, when this olivine erupted in the melt, was tracked up in the melt, the nickel went down again. And this kind of zoning is complex, but it's due to the mixing of melt and the important information we get out of there. We know that this olivine is recording the presence of two different melts that are simultaneously present in the system at that time. And then we can analyze here the core and know the composition of the one melt, and we can analyze this nickel-rich corona, and then we know the composition of the other melts. And then hopefully we can make deduction about the origin of the melt and what's going on and what's going to happen. So, talking about trace elements, what do they really mean? Here on the left side, there is a multi-element diagram. And I have with two olivine data. The one is a blue one, and I use this blue composition of these regular olivines that come out from typically hot basaltic mantle magmas that we think what is upper mantle. And then we have these other olivines that comes out in one more silica-rich magma that is cooler and erupts explosively. You see, the trace element patterns of those are really quite different. Here on the left, that is a logarithmic scale. And the whole project I'm doing now is trying to figure out why this fractionation, as we call it, of the red pattern happened relative to the green one, and what does it mean, and what indication it has from the mantle. Also, same this plot also on here on the right side, you see we were able to analyze the temperatures at which these olivine crystallize. So you can also see that the red ones that are fairly cooler ones. They're usually allowed below 1200 degrees Celsius and average about 1100 degrees, whereas these regular melts, the hotter and the basaltics, are at 1200 and above. The green is a transitional there. I just mentioned it here. And to show again how we do that, we analyze where we get these temperatures from. So we analyze the chrome spinel in the middle, and then we analyze these green points or the olivines around it, and we analyze the aluminium content in that olivine and the aluminium content in the spinel and a couple of other compositional parameters. And someone has calibrated a thermometer, and then we put it just into these equations they derived, and we are able to measure the crystallization temperatures of these melts. So this is how these two informations really come together. We know already that this red fractionated pattern comes from very silica-rich and cool and explosive magmas that erupt. And so we need to start now to connect this. And one of the questions is arising that as these olivine trace patterns in the red ones, in the red olivine are different because of the lower temperature. And here I want to introduce the concept of the olivine melt partition coefficient. It's a very simple ratio, namely in the case of nickel, is the concentration of the nickel in the olivine divided by the concentration of the nickel in the melt. This gives us the so-called partition coefficient. The nice thing was, if this partition coefficient was only a function of the composition of the melt, then we know that we can analyze these elements in the olivine and calculate or make deductions from there on the compositions of the melt. The hitch, however, is that these partition coefficients are not only a function of the composition of the melt. They also depend on melt temperature. They can depend on the melt water concentration, which is really a problem in the arc magmas I work on because they usually have elevated melt water concentrations. They also depend on the melt oxygen fugacity. It's a parameter that measures the amount of free oxygen in the melt that also changes in different magmas. And they also can depend on the changing melt SiO2 or MgO concentration, which are indicating a measure of polymerization of the melt. As again, as nickel, this is a parameter that is fairly well studied. So we see on the bottom here is the melt MgO, which goes up in the right direction. Usually the more mafic the melts are, the more magnesium-rich the melts are, the less silica they have. Towards the left, the melt silica goes up. So that means also the melt becomes increasingly more polymerized. And even without changing the nickel concentration in the melt, this partition coefficient goes up only by increasing melt polymerization. What that means that if I have the nickel content of the melt, it's all the same, but if I have a cooler melt, the olivine is going to take up more nickel. Right? That's really one thing that is well established. So I cannot just take the nickel content from the olivine and go back to the melt. I have also to consider the melt composition, and I have also consider the melt temperature, because you see this arrow upwards here. It means that also when the melt gets cooler, this partition coefficient is higher, and the olivine just takes up more nickel. Again, if you have the constant nickel content in a melt, and all what you change is either the silica composition of the melt or the melt temperature, the olivine will have different nickel content as it crystallizes. And this dependence of this partition coefficient on the melt, not only on the melt composition, but only on other parameters, in a way, it's a blessing. Because when we know that certain elements are sensitive against these parameters, we are able to get information out. This is the absolute advantage of this, because not all elements that I showed will react equally to these influences of the melt temperature. Some elements are pretty indifferent even against the melt temperature, and whereas, for example, an element like aluminium is very strongly dependent on melt temperatures, perhaps an element like yttrium is not. So the same is for water and the oxygen capacity. But at the same time, this is also a bit of a curse almost, because we can only get out this information when we have an idea how quantitatively and qualitatively the olivine composition is really influenced by this changing variable. And that is a part of a conundrum, because these quantitative influences of temperature, water, and oxygen fugacity, and so on, this is usually done by experimental studies, which are done by experimental specialists. I have no training in this direction, so I need to collaborate with colleagues who do that. But these colleagues want also to have a reason why they should start these experimental studies, which are very time-consuming and expensive. So we have also the possibility going into another approach, namely in doing empirical field studies and demonstrate that these experimental studies are very worthwhile doing. And this is also what my project is about. Unfortunately, I cannot yet go into the experiments, but I hope with the experimental studies we are doing that we can show that finally the specialists, these experiments are worth doing, and hopefully also the analytical progress is then, by the time it's so far, it has progressed so far that it can be done. Anyways, it's really early days now. And where the area where I'm doing my studies, I'm sure I shouted that before, is really olivines in the Trans-Mexican volcanic belt, simply because it's a region we have worked now for many, many years. We went out into the field. We sampled here composite volcano, Popocatépetl, found olivine furic rocks from Popocatépetl, as shown here in gray. And then we went to the monogenetic fields and sampled many of the smaller monogenetic volcanoes, which commonly also have olivine. We obtained a lot of bulk rock data and isotopic data and trace element data from the bulk rock. And we also run a couple of isotopic analysis on the olivine. We use the helium isotope, the oxygen isotope, the osmium isotopes. Was a very important information. We can measure these on the olivine directly, and they tell us really these are olivines that are consistent with an origin from the mantle melts. And we're using this set we developed ourselves, and we know now excellently well for diving deeper now into these advanced trace element analysis of the olivines. So in this project, we have about 35 samples. That's what I showed here. For each sample, I made a small histogram showing, showing here the forsterite content of the olivine, which is essentially the magnesium over iron ratio in the olivine. And we know the higher it is, the more primitive, as we say, is the melt, the more mantle-like is the melt. So you see this dashed line here at about 88 This is an approximate line that tell us to the right, these are the most primitive olivines, and you see we have many of these in the individual rock samples that lie to the right of that side, especially here at Popocatépetl, a major andesite volcano, but we find high phosphorylic olivines. And we also have these olivines from different compositional series. The one is the red one, or the calc alkaline. These are the very typical calc alkaline magma series that erupt in organs, that erupt so explosively. There is a subgroup of some that is shown in this lilac color that have a couple of special signatures. That's why we distinguish them. Then we have this green group, which are not so arc-like, also they erupt in close vicinity to all of this calc-alkaline rock. And we hope from them, perhaps they contain information on the mantle before it changed during the subduction. I will come to that later, what I mean by that. And then we have these blue groups. This is a group from behind the Mexican volcanic belt, which show no influence of the subduction setting we are working on. And the project is fairly simple. We just pick out the olivine, map them, see where the information is, put the laser on, put the electron microphone, collect the data, and then we compare the composition from the olivine to the melt and see whether they are systematic or not. It's fairly straightforward. I want to talk a little bit about results we are already getting. You see, this is, sorry, this is again the phosphorite content here on the x-axis. And on the y-axis is the nickel content. I'm sure that this is a mid-ocean rich basalt. It is oceanic basalt. They have also olivine, and they have usually very lower nickel contents. And as we know, the upper mantle composition, this is what we expect. And then these Mexican arc olivines have way higher nickel. So there must really be something happening why the olivine nickel is so high. It's cooler, that could drive up the nickel. Now the melt are more silica rich, that could also drive up the nickel a little bit. But essentially, we did the calculation in a very recent paper. It requires very nickel rich mantle melts from the mantle. And how do we produce so very nickel rich melts? And this gets us in the overall recycling. The Mexican volcanic belt sits in a so-called subduction setting, where the slab are subducted at the trenches, and then we get some material transport back from the slab. It goes back into subduction volcanoes, which are known to be very silica rich. They form the ring of fire. They erupt really, really explosively. But we know that some of the slab is also tracked deeper to the mantle core boundary and may come up in the source of interplate volcanoes. But one very important thing is that these slabs that subducted here at the trenches has chemical material that is out of equilibrium with the mantle. By the time it gets reacted, it starts to react with that mantle. And that's what we try to show in that other cartoon from a cross section. Here in these arrows here below, we indicate the silica-rich slab flux. And essentially, the more you get, the more you will change the mantle. I mean, in the beginning, you get a very little, and you have the mantle peridotite. This is a typical mantle composition lithology. sitting here, and well, they form a melt from peridotite that would still crystallize low nickel olivine, but then you put in again silica-rich slab flux and silica-rich slab flux, and then the mantle begins to react. So what could happening that we form pyroxenides because we add silica, and if we add silica to olivine, it changes, it becomes a pyroxene. And the pyroxene has less capacity of retaining nickel in the mantle. It puts it in the melt, and this is one. So melt from pyroxenide is thought to be nickel rich. We have also the possibility of exchange by diffusion. So this mantle here, the green one, is very rich in iron and nickel and magnesium. And we have here a silica-rich slab melt percolating through the mantle, which is very depleted in iron, nickel, and magnesium, then it's going to uptake. The elements are starting to diffuse from the wall rock here right into the melt. I mean, that's the essence of that. There are various ways to make nickel-rich melts, but they all of them do absolutely require that we have a silica-rich slab flux coming in, changing, reacting with the mantle with which it is not in equilibrium, and then create something. And the olivine are telling us that these nickel-rich melts are there, and that I think that was a really, really nice result. Depending, regardless of the detail about these melts are reacted, it's always a mechanism of reaction of these recycled flux from the slab and the mantle. And we think that these melts that are finally reacted are also likely silica-rich and cooler, because the slab flux also brings in a lot of water into the mantle wedge, which again lowers the temperature of these melts. And then another thing I wanted to show, it's also important when you form this very nickel-rich, silica-rich silicic melt from the mantle, they must also get up here from the mantle. So if I showed this in the brown color, these are the nickel-rich melts, and then they go up in here and then come out in a volcano to form high nickel olivine. But if you have the bad luck, you have still one of these high nickel melts in the mantle, and then they get stuck in the crust somewhere, and they mix with melts that come from other parts of the mantle that are not yet as reacted. Then this high nickel signal can also become easily lost. And in that context, the Mexican arc is a really, really good setting because it has extension, and it does promote the ascent of kind of mantle melts that can ascend rapidly through the crust and can bypass these reservoirs where often melts are stored and mixed and overprinted, and any mantle signal might be lost from here. Okay, so that's nickel. It's a very interesting element. We continue to study it and to see with what it might correlate in the olivines. We know already a little bit about the olivine calcium, another element we can measure in the olivine. And you see here again the olivine forsterite content, going here up high to 90. Then the mid-ocean ridges, they have far more calcium in the olivines than arc magmas. That is data I collected from the literature, probably not in very good quality, but we have this high quality data here from the Mexican arc front, where the calcium is also much lower than of the olivine. And the big question right now is that some of my colleagues think this is due to the higher meltwater content of these arc magmas, which are typically more hydrous. And this changes this partition coefficient in that it lowers the partition coefficient, and thus the olivine have lower calcium despite having a similar melt calcium content. I'm not so sure. I mean, this might be contributing, but calcium is also an element that shows us whether the mantle might be depleted relative to the more mantle. And if we had a depleted mantle, this has deep consequences for the formation of the earth magmas. We can create in a depleted mantle, for example, this a typical calc-alkaline differentiation joint in earth magmas that is unique to these earth magmas. And many people think it's created in the crust, but if you can prove that the calcium is really owing to a depleted mantle, we have the option saying it really comes right from the mantle and is right a consequence of recycling. And also the more depleted the mantle is, it also follows from mass balance through the earth that more elements are coming out from the slab that finally make it through the earth. So this is something we are currently trying to investigate by getting acid trace elements on that are not sensitive to water, something like titanium or yttrium or terbium or zirconium, which we can now measure in olivine. So I'm really very anxious for these results here. And finally, what we know already, we have recently analyzed high precision manganese data in the olivine. And again, here phosphate content in olivine versus the manganese content in the olivine. And you see that the MORP, the mid-ocean ridge, which is really the epitome of mantle melt, what they should be, are systematically offset from the Mexican volcanic belt. We tried to model this by melt extraction, but it goes in the direction of these black arrows. It goes to higher phosphorite, but it's not changing the manganese. And the best explanation for that, we are coming now up with that, is that the Mexican mantle beneath Mexico is distinct from the mantle beneath Moro. That is one possibility, but we still need to have more data, not only from Mexico, but from acid settings, that we can really prove that point, that there might be a systematic means, a really first means in a way, to look to track mantle composition. It's awfully difficult to do it with volcano rocks because they get so changed in the crust. But this might be a possibility. We need to follow up. I was only yesterday at HEU. I presented my poster, and one of my colleagues said, well, manganese is such a boring element, and suddenly we have a possibility maybe to make good use of it and understand more about the mantle. So that's really perspective. So what we are doing now, we test each single olivine trace element for its potential as tracer of mantle melts. We need to understand how they change with the melt composition, the oxygen for gases, the water, and the temperature. And we are just now collecting all these data from the Mexican olivines and interpreting these results. And it would be lovely if this would lead one day, convince one of my experimental colleagues to dive deeper down into this really time-consuming and expensive partitioning experimental studies that help us to understand, to confirm or to test the partitioning and to test these results. But all the time, I think it looks like pretty good right now that we see results, that we can see mantle processes that will ultimately help better to understand whether these highly silica-rich melts explosively, oh my goodness, printing errors, that we can finally, a big part of these melts does come out of the mantle and are not entirely created in the overlying crust, and what that means also for the mass transport through the abduction zones and through the mantle. So, thank you very much.
Thank you very much, Susanne. The only thing I'm thinking about right now is whether you see or can see any differences in terms of time. Over
Oh,
geologic time, is there any differences in the compositions?
we looked at these monogenetic volcanoes, and some have nice time series, and we know from the bulk rock there are changes in time, and already begin to see also in the olivines there are changes in time. This monogenetic volcano is typically a short lifetime from a few years, so we can really see what we interpreted already in the bulk signal as a changing mantle source this monogenetic volcano is tapping into, and we see the same thing in the olivines. So we can really directly test this in our empirical studies. Time series from composite volcanoes are very difficult to get. They're just a mess, you know. Erupting, explosive, everything tumbles through each other. But this monogenetic, some of these monogenetic volcanoes are really, really nice.
Thank you. Okay, we appreciate your sharing your expertise and time with us today.